All right. So for the transformer equation, we will have to know the concepts of alternating voltage, electromagnetism, and magnetism in general, because we'll see how this topic is sort of an integration of all of these individual concepts at the same time. Now, what is a transformer? We've used this terminology a lot of times in our daily lives. Transformers for different electric currents, transformers in our houses, transformers at a large scale in power grid stations. Um, Transformers, what they essentially do is they convert current, they sort of change voltages, um, and whenever we require a certain change in current or a certain change in voltage, we use this device called transformers. Okay, so the exact exam-based definition of transformers would be that it is a device that changes high alternating voltage at low current to low alternating voltage at high current and vice versa. So what we essentially say is that if you have a high alternating voltage and your current is low, a transformer can convert this high into low and this low into high, a high voltage to low current, low voltage, and a low current to high current, and vice versa. Similarly, if you have, for example, a low alternating voltage and a high current, a transformer will convert this low alternating voltage to high alternating voltage and this low current, this high current to low current. I hope that makes sense, Raghav.
Yes.
So it is going to convert the voltages and the current. So we're dealing with I and V over here, voltage and current. Okay. Up now, what happens here is, so it's important for us to understand if you have, let's say, power station, and this is basically maybe a house. Now, this power station is supplying voltage to this house and so many other houses likewise. The voltage that's produced at this power station is maybe a lot more than the voltage that you require at your house. Let's call it VA and let's call this one as VB. So VA is the voltage that's essentially produced at this power station, and VB is the voltage that is required by your house or any other house maybe. So you need to, obviously you cannot supply this entire voltage to a house. Appliances, if they have a certain voltage rating and you supply more voltage, they're gonna burn. It'll burn the appliances. So it's very important that you quantize these values and supply the values of current and voltages that are needed. So that is when a transformer will help you. This is where you place a transformer. Now, a transformer, what this transformer will do is it will convert this higher voltage into lower voltage, this VA into VB. So this is one example of how a transformer is used. Now we need to understand what is the process, how all of this happens. If if you have a transformer over here, what exactly is the mechanism of it that it converts this entire voltage into a lower voltage? Or for example, even if let's say you have a voltage supply that's lesser and the appliances or the household it requires more voltage, the transformer is going to is going to increase the voltage supply to high alternating voltage as well. What is the mechanism, how this happens? This is what we're going to study right now. So um up if you supply, now why do we actually require the use a transformer over here? Now if you just think of it, if you supply that entire voltage, it's going to cause damage. If you supply lesser voltage, it might not just run the appliances. So essentially you're reducing the heat energy lost, because when electricity is transmitted from power lines to power stations to the grids, there are a lot of chances of electricity being lost or energy being lost basically. So what we do is we use transformers to sort of align these supplies and to reduce the losses of heat energy. So this is one advantage of using transformers, apart from all of the other advantages that you obviously supply to a very accurate rating of power that's required. The reduction in power losses is another advantage of using transformers. So a transformer, if you look at the mechanism or the built-up of a transformer, it's made of a primary coil, a secondary coil, and an iron core. Now let's see what these coils are and what's the function of these coils in the core. Okay, look at this diagram. Now, this diagram is going to help you understand the mechanism of a transformer. Let's first of all look at this bigger solid thing that you have, this gray solid perforated block. This is an iron core. This block is made up of iron, and this is called an iron core because it's placed right in the center of a transformer, and the entire process happens around this core. Okay. So the soft iron core is important because it focuses and directs the magnetic field from the primary to the secondary coil. It sort of concentrates the magnetic field. This is the primary coil. Now, this could be like a bunch of copper wires wrapped around this side of the iron core. And this is a secondary coil. This could again be a bunch of copper wires wrapped around this side of the iron core. Now, because there is magnetic field between these the primary core and the secondary core, why is there a magnetic field? Because there's alternating current, and what this core does is this core sort of concentrates the magnetic field just to this particular position, all right, just to this particular place. Now, why do we need a soft iron for a core? Because a soft iron is a material that can be magnetized easily, and this material can be demagnetized easily as well. Okay, so you need to have a material that is easy to magnetize and easy to demagnetize. This is why an iron is like the best choice for this core. Now, there's one thing that you would have noticed, that this particular red patch is smaller than this particular red patch. The secondary coil has more turns of copper wire, whereas this primary coil has less turns of copper wire. Why is that so? Now, this type of a transformer is called a step-up transformer. Why do you call it a step-up transformer? Because number one, the first identification of it is but just by looking at the primary and secondary coil. Because secondary coil has more turns, that means it is gonna increase the value of whatever value that is at the primary coil. It's just gonna increase that. If it's current, it's gonna increase the current, and eventually it's also gonna increase the voltage. A step-up transformer sort of increases the value. And a step down transformer would, on the other hand, have lesser coils, lesser turns on the secondary coil side, which means it is going to decrease the value. We're going to call it a step down transformer. So these are two types of transformers, and the functions are exactly the opposite of each other. Ragda, any questions so far?
Thank
Okay. Now, what happens is the primary coil, there is an alternating current, and it also produces alternating voltage. Um, and this alternating current and alternating voltage, they produce an alternating magnetic field inside the core. And obviously, it's going to change the magnetic flux linkage as well. We've studied magnetic flux linkage, we know what it is. So now, because of the alternating current and because of the alternating voltage, magnetic field will be created, and this iron core is going to allow this magnetic flux linkage to change, and this changing magnetic field passes to the secondary coil through the iron core. So at what happens at primary coil, a magnetic field is created. That magnetic field is then transferred to secondary coil through this iron core. Okay, and the result is that the magnetic flux linkage changes in the secondary coil, um, because of the Faraday's law of electromagnetic induction, and that as a result induces EMF. So if you want to categorize it down, number one, what's happening is at primary coil, magnetic field is being produced. We need to understand that field is being produced. The second step is the transfer of that field. Now iron core comes into play and the field gets transferred to secondary coil. And at the secondary coil, what happens is that flux linkage changes, and electromagnetic induction happens. EMF is induced. So why is the EMF induced? You know the process, because of the changing flux linkage. So these are three major steps. This happens at the primary coil. This happens at the core, or the core helps uh, with this process. And this is what happens at the secondary coil. So you need to know these three things that are happening. And the entire mechanism of a transformer is based on these three major processes. Now, EMF that is produced at the secondary coil in return produces an alternating output voltage from the secondary coil, and the output alternating voltage is at the same frequency as the input voltage. Okay, there is an output voltage as well, and this is the transformer equation. Now, this equation, this N is the number of turns of the secondary coil, NS. NP is the number of turns of the primary coil. Vs is the voltage at the secondary coil, and Vp is the voltage at the primary coil. So NS over NP equals Vs over Vp, right? Number of turns. Now, number of turns at these coils directly correlate with the voltage being produced. So now this is what you should be aware of. Okay, let's say if there are 100 turns at secondary coil and there are 50 turns at a primary coil. So the voltage, if you want to find out the voltage at a secondary coil, considering that the voltage at primary coil was 20. So you're going to use this equation. 20 times 100 is going to be 2000 equals 50x. This is going to give you 400. 40, sorry. Okay. So what's happening here is, यहाँ पे your voltage has also increased because of the number of turns of secondary coil. And look at the ratios that are sort of changing. 50 to 100, 20 to 40. This was increasing by a factor of 2. This is also increasing by a factor of 2. So as you change the number of coil, the number of coils is gonna change the voltage with the same ratio. That being said, the next thing is current. Now, how do we include current in the equation of this transformer? That is when current is always included when a transformer is 100% efficient. This is very important for us to know. Another step of this equation that we generally forget while studying this topic is Ns over Np is equal to Vs over Vp, and that is in return equal to Ip over Is. Remember, this is inverted. This is not as secondary and primary ratio in the previous two quantities. This is inverted, IP over IS. And this entire thing is only possible when a transformer is what? It is 100% efficient. All right. But this is the thing that you need to remember over here is that whenever you're including current, the current at primary coil will be written as the numerator position, and current at the secondary coil will be written at the denominator position. This is the only difference that it makes when you have a current over here. So this is the extended version of the same equation, but this is the basic transformer equation that we're talking about. Any questions?
Right.
Now, generally, a step-up transformer increases the voltage of the power source where number of secondary coil is greater than the number of primary coil. We know that this is a step-up transformer, that the initial value will be lower and the final value will be greater. Similarly, a step-down transformer is the one that decreases the value. Number of primary coils will be more than number of secondary coils. The initial voltage would be more and the resultant voltage would be less. So generally, a step-up transformer is used between power station and transmission lines, where generally power station supplies lesser voltage, and then you increase it when the voltage is applied to transmission lines. And then a step-down transformer is used between transmission wires and buildings, because generally you don't need a very high value of voltage when one particular voltage is applied to the buildings. So it is generally more in the transmission lines. You step it down, you decrease it, and then that voltage is applied to the buildings or the houses. Let's look at this work example. A step-down transformer turns a primary voltage of 5 kilovolts into a secondary voltage of 100 volts. Calculate the number of turns needed in the secondary coil if the primary coil contains 3,000 turns of wire. So now primary voltage is 3.5 kilovolts, which is going to be equal to 0.5 times 10 to the power of 3, 1, 2, 3. So it's going to be equal to 500 volts. So you've got 500 volts over here. Uh, voltage at primary and the voltage secondary is supposed to be 100 volts. So we're basically converting this 500 volts into 100 volts through a step down transformer. So always write down the data. Just know what you have for these type of questions. This is a step down transformer. So you should know what your initial voltage is. Voltage primary is how much? It is 500 volts. And remember to align the units as well. And voltage secondary that you have over here is 100 volts. So automatically, even by looking at the voltage values, you can easily guess that you're getting, because the resultant value is lesser. So it is a step down transformer. And yes, the equation is correct. Now, the number of turns at primary coil is how much? NP is 3000. And the number of turns at the secondary coil is what we're finding. Now that you know that it is already a step down transformer, so the number of turns the secondary coil will be less than the number of turns at uh, the primary coil. So number of S would be, sorry, would be less than the number of turns at primary coil. We've established this information from the concepts that we already know. And now we're going to simply put in the formula NS over NP equals VS over VP. Now, number of turns of secondary coil is what we're finding. We're going to keep it as NS. Number of turns of primary coil is 3000. Let's just put that over here. Vs is the voltage of secondary, which is 100, and Vp is the voltage of primary, which is 500. We've got all of the values. 500 times Ns equals 3000 times 100 is 300,000 divided by 500. Zero's gone, and this is going to be 600. So now the number of secondary turns are basically, sorry, 6,000. Yeah, there's 6,000. Yeah. So 6,000.
6,000 नहीं होगा, 600 ही होना चाहिए.
Just a second.
Shouldn't it be less?
Yeah, 600. ठीक है. Yep. वो हमने क्या किया था? It was 3,000 divided by 500. Sorry, 300,000 by 500. So 3,000 by 5 is 600. Correct. Now, what is this 600? This is the number of turns of secondary coil. So number of turns of secondary coil is 600. And number of turns of primary coil was 3,000. So look at the ratios as well. It was 100 to 0.5. So 500 was the secondary voltage and 100 was the primary voltage. Sorry, ulta. 100 was the secondary voltage and primary voltage. So I hope this is pretty much clear now. Just this formula is going to help you with a lot of the questions. Keep in mind the ratios. Keep in mind what a step down transformer does and what a step up transformer does. It is going to make these concepts a lot easier to understand. If there's any question from this lecture, Rakta, you can let me know right now.
There's not too much.